I'm very interested in thinking about how we can design robots that are both safe, robust, and very interactive. So when we're really thinking about putting these robots out into the field or out into public spaces where they're actually working with people, we want to make sure that they can, one, do their jobs effectively, and two, sort of facilitate nice interactions. And in my lab, we work on lots of different applications. We work on things from autonomous vehicles to manufacturing, crowd navigation, things like that. As you can probably guess, I am not here to talk about those things. So today we're going to be talking about agricultural robots, and specifically we're going to be talking about mostly this small under canopy robot as visualized here. It is sort of Illinois' flagship agricultural robot. So we'll be talking about this Terrasentia robot by EarthSense. So as a quick introduction, we're very motivated by this sort of idea or this broad vision of having this farm of the future where we have this fleet of robots that can go and perform very precise actions out on the field. So we have two sort of key main motivations for this. First, at least in the US, agriculture is facing this pretty big labor crisis. So we're trying to develop automation that can help sort of fill in some of these roles. And again, help alleviate some of the pressure that farmers are currently facing. The second is really trying to see how we can promote more sustainable practices through precision agriculture. And again, I'm sure most of you are all very familiar with this, so I won't push it too hard. But one of the big things that we're pushing, again, is these sort of small under canopy robots. And one of the big motivations for using these small robots is they'll have more precise actions, so they can more precisely collect data about specific crops. Since they are under canopy, they can get a bit more information. And they'll also have sort of closer access to the specific plants that need to be fertilized or specific weeds that then need to be pulled or have stuff applied to them. So by looking at these smaller robots, we're hoping that we can do things that are a little bit more precise. We don't have to worry about these sort of large equipment that are both very dangerous to work around, but also sort of do sort of blanket spraying or sort of blanket procedures. So again, we're sort of relying on these small robots to sort of perform these actions for us. Now, we sort of have this image here, which again, we sort of see these robots doing everything and whatnot, but this is a great vision. And one of the things that we first started doing when we started working with these robots is we started thinking about if there is some way we can kind of codify what we want them to do and sort of what the development process should be. So one of the things that I've been working on with Girish Chowdhury is working on coming up with something like a levels of autonomy for field robots. So I think people are in general very familiar with the levels of autonomy for field or for autonomous vehicles. So this is sort of a standard thing that everyone thinks about since autonomous vehicles sort of are on top of mind for a lot of people. And what the nice things about this levels of autonomy is it kind of gives you this sort of nice progression that we can start using as a guide for development. But it also gives us sort of two key insights. So the first insight is it gives us some idea of what the capabilities of our robot should be. But these are all defined by the second point, which is actually what is expected of the human user. So if we look at these levels of autonomy, we can actually define them by what we expect the human to do. So these level 0, this is just our sort of standard car. We expect that the human will be doing this sort of manual driving. They're in total control. And as we sort of increase this level of autonomy, we basically relinquish responsibility from the human. So there's some partial control or partial automation where they still need their hands on the wheel. They still have some things to do. Eventually it moves to the point where they can have hands off. And again, we kind of move to this point where they no longer have to look exactly at the road and they can start doing other things. So again, this is sort of nice because it both gives us some insight about what our expectations of the autonomous system should be, but it also gives us guidelines for the human. So in field robotics or broadly agricultural robots, we don't have the same structure in the environment as we do for autonomous vehicles. So it's actually a little bit harder to strictly say what the capabilities should be, since we have such a wide variety of tasks every farm is a little bit different, so we can't really say that as much, but we can define things by sort of what we expect the operator to actually do. So we can basically sort of move this down to the point where we have basically these robots fully in control, or fully controlled by a human. We can basically release this down to where we just can do some hands-off. They just need to, monitor their robot. One where they can let it be a little bit more independent. And finally, we can get to the point where we can get to the sort of one-to-many control or fleet management in some sense. And to sort of give this a nicer visualization, we can kind of see a different take on this sort of farm of the future with this fleet of robots, where we want to move from this sort of one-to-one type interaction, which is, we're a little bit past that, but that's sort of state of the art, where you have your robot, it is being monitored. Which is good because it can still perform more precise actions, but you're not really alleviating any of the pressure on the labor crisis or on people. So you still sort of have one robot to one human. And it's really until you get to this point where you can have one person monitoring many robots, where you can get to this point where you're starting to get some real value. And this is where you can start seeing returns on investment. This is where you can really see the point of where the farmers or whoever might want to actually adopt these systems. And again, hopefully this can get to the point where it's very distributed and you can really sort of scale spatially. So there's sort of two key elements to this. So far, I've been talking a lot about sort of the role of the human, again, because we kind of want to push this up to this point where we can get this sort of one-to-many type interaction. But this also does tell us that, again, for our specific tasks, what we actually want these robots to do. So we can start also thinking about making these robots robust enough that we can actually enable this one human to supervise many. So for the rest of this talk, we're going to be basically talking about some work that we've been doing to make the navigation stack for these robots more robust, so we don't basically have to have them be babysat all the time, sort of monitored by a human. So we're going to be sort of going through and sort of pushing these this navigation stack up and sort of developing that so it's more robust and can handle whatever might pop up in the field. Okay, so to give a little example of what these robots in particular do, these are, again, small under canopy robots, and they're primarily designed to go up and down corn rows. So in Illinois, we have lots of corn and soy. So we are very motivated by these commodity crops. So again, they can go up and down these rows. They can collect data. They also have attachments, so they can do sort of precision fertilization, as well as have some weeding attachments. I sort of stop it here usually because you can see this is that case where you actually have that person, they're monitoring the robot, they have control, they can save it if things happen. So this case is an example of this one-to-one. So these robots in general are getting actually very good. They can now, I think the precise number is they can travel over 100 or 1,000 meters with no interventions. However, they still get into failures. And this failure looks a little bit silly here. It just sort of runs directly into the corn row. But these failures do happen. So what we're mostly going to be focusing on today is figuring out how to identify these failures, because it's actually quite difficult for the robot to really identify when it is in a failure mode. And this can really help us start thinking about how it can start asking for help, how it should interact with that human supervisor. Okay, so one of the big challenges with looking for failures is actually sort of a broader part of the bigger challenge that we have in agriculture. And it's that we find that we have this sort of data imbalance. So when we think of normal operation of these robots, and we sort of think of all of that sort of time we're traveling in this sort of time series of moving up and down the rows, if we look at all sort of the instances where we are in normal behavior, we get lots of data for that. However, with these failure events, there are sort of these one-off events. They sort of end this trajectory typically. So we typically don't get many samples of that. So if we want to try to identify failures, we kind of have this problem, which again, it's data imbalanced. So if we're trying to identify or classify when we're in a failure mode, it's very difficult because we have such an overwhelming amount of positive examples that it becomes very hard to sort of identify these rare events. This is further hard because the way the robot fails will continue to surprise you. So no failure is exactly the same. So it's not even that it's sort of uniform, but we have many different types of failures. So coming up with good ways to basically balance this data, we have to do something that's a little beyond sort of standard practice for learning-based approaches. The other thing that's a little bit tricky about this is these also are sort of high-risk events. So even though we don't have many points, they hold a lot more weight. And these are really the points that we really care about here. So again, this is something that really helps the feasibility of these robots actually being deployed. And even though for the most part, since it is a small robot, we don't really have any huge safety issues, but it can run over plants, it can sort of harm the field, and it could possibly harm people. So we sort of have this, this issue where we need to sort of come up with tools and approaches that can handle this data imbalance and really make sure we're capturing these failure cases really well. So as I mentioned, one of the sort of, again, key issues with this is these failures here are not all the same. So it's not like there's one exact failure that we're trying to capture. There are many sort of different types of behaviors. So the first thing we did to start sort of going through this is we tried to go through and sort of classify or use some of our domain insight to try to come up with different categories of failures. So here's some of the things that we found that sort of typical behavior of these robots. So here is just normal operation. Again, this is where most of our data comes from because we're working on this time series. For the most part, it is collecting this sort of good examples of scenarios that it can handle. What's a little bit interesting about this is you can see it is very cluttered. We have the leaves sort of blocking a lot of the view. Even if there are some weeds in the way, a lot of weeds don't necessarily impede the navigation capabilities. So we kind of have this this sort of normal operation that, again, even from a human's eye view, could look like it could be something that could be very hard to traverse. So the next type of failure that or I guess the first type of failure that we identified was this row collision. So this is the example that we sort of showed before. This is basically when the robot just runs into one of the corn rows here. This can be due to either having an incorrect estimate of the lane or the row orientation, or it can come from slippage in the wheels here. The nice thing about the row collision is it is actually a very easy failure to identify. There's an easy corrective maneuver. You can back up, reorient, try to get a better estimate of your row, and then you can proceed forward. There are some other examples of failures that we found, and we basically broadly classified these as an untraversable or traversable obstacle. So this one, it's a little bit hard to see, but I think it does actually capture what can happen in the fields pretty easily. So here we have very low visibility, and you'll see we kind of run into something here. So this point here, or you'll kind of see there's something blocking in the middle. This is actually a corn stalk that is growing in the middle of the lane. And this obstacle is untraversable because basically no matter what the robot does, it cannot go through it. So this is an instance where unless it basically just turns around and calls it a day, it cannot actually proceed down this row or collect more data or basically complete its task in this situation. The final example that we have is traversable obstacles. So this is something where we have some obstacle that it could come over, but it at the current speed or given basically the way, sort of the angle of attack, it actually can't. So in this one, you can see there's a corn stalk that has fallen over. So it is blocking the path. Currently, it can't get over it, although it potentially could get over on its own. Traversable obstacles or untraversable obstacles don't always have to be these sort of solid objects as well. We can also categorize mud as this, basically something where it gets stuck as well. So these are the different types of failures that sort of we identified and started thinking about. But again, we sort of have to think about how we can actually classify them, since again, we have all these issues with data imbalance and some sort of the fundamental issues with having to deal with this type of data that is very noisy, very unstructured, and sort of has a lot of variability sort of hidden within it. So what we decided to do is trying to see about how we can cast this as an anomaly detection problem. So as a proxy for this sort of failure detection, we're trying to say, is this sort of a normal event or not? And if possible, can we break that down a little bit to give some more insight to the type of collision that it is? So the nice thing about casting this as an anomaly detection problem is this sort of inherently consider some of the concerns with this sort of underrepresented data or these low probability events, since that is what anomaly detection is meant to do. And we started doing this by basically collecting a bunch of data from these operators who were monitoring the robots. Whenever they were monitoring or testing their robot, they could basically identify or label our data. When a failure occurred, give us some insight about what happened, and then this basically provided us with some data to work with. And again, the hope is that if we can start giving some insight to the failures that we encounter, we can again start really thinking about how we can better enable some sort of smooth interaction with the human supervisors. So typically for anomaly detection, if you look at this from a very classical sort of signal processing type perspective, you'll typically start looking at things like distributions. You'll try to find those tail events and sort of figure out where it is there. For these sorts of applications, though, it's very hard to really get those distributions. So we typically have to apply some learning since we are basically just working with highly noisy data. So the sort of very classic approaches for anomaly detection are very challenging to work in practice. So to do this, we're basically going to look at some other learning architectures and learning approaches to basically come up with an anomaly detection framework. So one of the sort of more naive approaches that you could do, since we have this labeled data set, yes, it is imbalanced, but there are sort of ways we can subsample and work with that. We can basically cast this as a classification problem here. So we basically have our observations. We pass this to some classifier. It can be whatever your favorite type is. This can either be, again, this sort of very traditional find your probability distribution, find the probability and do some thresholding, or this can be something a little bit more complicated like a neural network, but you can do some classification technique. So that's sort of a naive approach, and you can use this as an anomaly detector because of the sort of way we're formalizing the problem. However, this typically doesn't do that well in practice. Again, because of the issues we talked about before, it's just very hard to find explicit patterns in the data without a little bit more structure. So one of the things we started looking at was basically more structured approaches to learning distributions. So there's some work by Dae-Hyung Park, who basically showed that basically if we just look at this purple section here, one good way to do anomaly detection is to basically take a reconstruction-based approach. So they use a variational autoencoder, or a VAE, to basically take all of their data or take their observations and code this down to some latent feature space and try to reconstruct that output here. And the basic assumption here is that for normal data, or for most sort of instances that we have, for instance, the sort of normal operation when everything is good, we'll probably get a very good model. So if we have sufficient data and we do our due diligence training, we'll have very good reconstruction of sort of this nominal data here. So basically this good behavior will do a very good job of reconstructing it. So online, we can take in some data, say a LiDAR point cloud from our robot, we can pass it through, reconstruct it. So try to basically recreate that same image, and we can look at the error between our reconstruction and the observation. And if we have a relatively low reconstruction error, we can say that this is sort of normal behavior. If we have a higher instance of error, then we could say this is probably something that is out of distribution. So we're very good at basically reconstructing in distribution data, bad at out of distribution data. So just using this VAE type approach here, so just looking at this encoder decoder structure is a good way to basically just classify anomalies and not. And this was demonstrated in some pretty cool human in the loop sort of studies and whatnot. However, again, one of the things that we're really interested in is providing a little bit more information. However, we can sort of provide, use this classifier idea. So we can basically find this encoding structure that again is designed to reconstruct our observation here, and then pass this through our class labels here to basically give us more insight about the anomaly. So we can both run these simultaneously. So we can have some flag that basically just tells us if we are in the sort of mode of anomaly or not, but we can also try and get some insight about sort of what class or what sort of category of instance we are in. But we found if we actually train this simultaneously, we get much more better structure in our underlying sort of representation here, and it gives us much better performance in the end. But at minimum, at runtime, we can just basically run this branch here where we're basically getting out what type of failure we're getting. So one thing I mentioned was we actually do get something sort of intuitive out. So I mentioned we take our LiDAR point cloud and we embed this down to a latent space. So it's sort of nice if we visualize our latent space. So we say, let's project it down to two latent features. So we have Z1 and Z2 is basically where we're projecting this point cloud down to. If we uniformly sample this latent space and reconstruct it, we can get some kind of interesting observations here. So basically what we end up encoding is that in one of our latent features, we actually get this sort of openness of our point cloud. So we can see sort of on this lower end, we have a very sort of closed in point cloud, which indicates that there's likely some obstacles or something in front of us. And as we sort of sweep this over, we get this much more open point cloud, which means there's likely an open row in front of us. As we sweep down this other latent vector here, or latent element here, we actually can see we get this sort of swing of orientation from left to right. So what's nice is by doing this approach and by adding the structure, we actually get more insightful sort of work in our latent space, which again, in turn, actually helps us get very good results when we're trying to detect these systems here. And for the most part, this works very well. There are some instances where it does get outperformed by relatively basic methods, but overall it does quite well. So here we can see this operating sort of in real time. So here we have our LiDAR that we're visualizing here. We have the encoders here, so you can see what the robot is doing. And here's our estimate over the different classes. So we can see that it's going down the row. Everything is normal. It's having a good estimate of that. And it's continuing to go. Speed it up a little so we can get to something a little bit more interesting, because again, we'll get a lot of these normal instances. And then at some point it will get into a row collision, a recovery maneuver is performed, and it continues down the road. And since I'm running a little bit low on time here, very quickly, we'll keep on going. Those events aren't necessarily anomalous. However, we can test this on fairly new events. So this is when a grad student appears, something that is never seen before in the training data, and is still able to detect that this is a untraversable obstacle. And part of this capability is because we are using, at this point, only LiDAR data. So this is something that is very easy to define or to sort of capture, and it kind of maps nicely into what has been observed. And we can also connect this to some more active studies or active applications. So once you get into or identify a failure, which in this case is actually an incorrect label, so it thinks it's in a row collision, but it's actually sort of encountering this fallen over leaf. So this is an untraversable case. It can basically actively probe the system and try to come up with a better estimate here. So you can see it basically performs this recovery maneuver, which should fix the problem. It still runs into the crop here, or the plant, and it will slowly basically modify its probabilities and sort of come up with a better estimate of where it is. So it basically is updating its confidence by basically continually running into the plant, which, to be perfectly honest, is not a great thing to do. So we actually don't want to keep running into plants. So what we really want is something that is perhaps a little bit more proactive and perhaps a little bit more intelligent. So one of the extensions to this is to really start thinking about sort of extending this away from reactive failure detection. So here's an example of a failure that we would really like to avoid. So what's happening here, it's getting in a row collision, but as you can see, something kind of weird is happening. So this is the onlooker's perspective. So this is sort of a silly failure. Actually, it's not very hard to identify, but this is something that it would be really nice if we could predict before it happens, because this is something that we really just don't want to get into at all. So one of the things we also worked on is extending this, again, this sort of reactive online approach to a more proactive or predictive detection here. So for this, we introduce this method called PAD. So this is proactive anomaly detection. And basically the main difference here is we are basically also injecting a planned path into the learning process here. So this image up here is basically a bird's eye view where we're projecting our planned path from our model predictive controller that's basically going to maneuver our robot. So this is projected down to sort of this 2D plane. So you can kind of imagine we have some cornrows, something like here. This is our planned path. So we can now take this planned actions into account when we're thinking about basically trying to identify these, the future failures here. And one thing we found is that by looking at this bird's eye view sort of prediction or this image view of it, we actually had much more robust performance than just putting in sort of a sequence of points. But in this, we also looked at a little bit more multimodal approaches. So now we combine both the images as well as the LiDAR. And the goal here is to basically get more of a time sequence out. So we both want to be testing or saying over the next sort of future time horizon, when are we going to be safe or a normal operation? And when are we going to be in these failure modes here? And we do this by some voting method. Here. So basically we want to identify when things are good, when things are bad. And our estimate basically comes up with a sort of rolling average. So we kind of average things out so it doesn't become too sensitive. But a lot of the structure that we had before is taken from our previous approach. So when we test things online, we can now basically have this same structure, this sort of same insight, but again, now we can look into the future. So here's an example. So our method is on the bottom and just a pure LiDAR approach is on top. You can see the projected path and you can see it can handle even very complicated environments where a single sort of mode of just a single mode of sensing would basically fail, as in this LiDAR case here. And we can see we can predict a failure fairly early. So in this case, we were just showing the failure. So we weren't really going into actually correcting for it because we wanted to make sure it actually happened. But in theory, we can actually basically plan a number of different trajectories and pick the ones that have the lowest likelihood of failure. And again, overall, we do quite well, and we're able to have more robust performance than other comparative methods. Okay, so I'll quickly wrap up here. So today we talked about anomalous failure detections. So for systems where basically models or basically good representations of the environment or a complete data set are really hard to come by, anomaly detection or these sorts of sort of learning approaches that sort of enforce some structure and can handle imbalanced data can often act as a proxy for failure detection. So we proposed this SVAE approach as well as a sort of predictive variant to detect these different failures. But again, something that I've been hinting at occasionally is like, so now what? So what do we do now that we have this failure detection? And that's where we can actually bring it back to this original image where we can really start thinking about how this actually can help inform the user. So one, we can start thinking about when we actually need to call for help or when that user really needs to provide assistance. So in these sorts of cases, this is basically when the recovery maneuvers don't work or when we found some sort of obstacle that we've never seen before or don't know how to handle. So we can start really sort of both giving the robot a little bit more self-awareness and a little bit more sort of baked in intelligence, but we can also, again, facilitate that interaction. And as sort of one final thing, one thing that we have been working on is, again, sort of pushing this to thinking about how we can formally describe the supervisor here. So if we have instances where many robots are out in the field, maybe they're all failing, maybe they're not, we can start actually thinking about how to incorporate that supervisor in the loop and basically treat this as a scheduling problem to help that supervisor decide when they should actually help a robot, and if multiple robots fail, which hopefully never happens, but if it does, what is the proper order for this to happen? So there's a few different sort of naive approaches you could take. For example, you just go to the first robot that fails or the closest robot. But actually, if you model this as a graph traversal problem, you can actually think about how you can maximize overall team performance. And although not exactly relevant to the farmers, you can actually have very nice formal bounds on complexity and optimality, which is pretty cool. So if you formulate this as a graph, you can basically treat this as a variance of the traveling salesman problem. So some sort of cool other work there. But again, today we talked about how we can start basically injecting some awareness or some sort of failure detection modules into our robots, which can help improve navigation and really help us get to this point where we can start scaling up these robots. And again, hopefully really coming up with impactful ways to apply these robots at scale, both in terms of numbers of robots, but also sort of spatial as well across the field. And again, really hoping that we can push that sort of future farm where we have fully sustainable practices, and again, mostly autonomous farm. So with that, I'd like to thank all of my students and collaborators on this. In particular, I'd like to give a shout out to Tianchen Ji, who is the student who actually did all of this work. I'd also like to thank EarthSense, who provides our robots, and our sponsors from the National Robotics Initiative with the USDA, and AI Farms, which you will be hearing about in the next talk. So with that, thank you very much, and you can feel free to contact me if you have questions, or I will take them now.